Imagine a physical object that exhibits perpetual motion, moving forever without consuming or losing a single drop of energy. Curious, these diamonds are defined by their structure. Their atoms are locked into rigid, unchanging three-dimensional geometric grids. This is a property known as spatial symmetry breaking, where standard matter settles into a highly ordered, repeating pattern in physical space. In 2012, MIT physicist Frank Wilczek asked a strange question. If atoms can lock into a repeating structure across physical space, could they also lock into a repeating structure across time? This hypothesis created a problem for physicists. According to the Second Law of Thermodynamics, the rule stating that isolated systems naturally evolve toward maximum disorder, any system moving perpetually should generate entropy and bleed heat. By 2015, theoretical physicists published a strict no-go theorem. They mathematically proved that a time crystal existing in a closed equilibrium system is an absolute impossibility. Wilczek's idea forced a crisis in the field. Either time crystals were pure science fiction, or the laws of thermodynamics were missing a specific exception. This diagram illustrates the solution: non-equilibrium matter. While time crystals are impossible in a static environment, they can exist in a Floquet system. A Floquet system is periodically driven by an outside force, like a repeating laser pulse. Think of tapping a bowl of Jell-O. If you tap it twice a second, the material reacts exactly twice a second. Standard-driven systems react in perfect one-to-one synchronization with their incoming energy. But a time crystal does something unusual called a subharmonic response. When you pulse it twice a second, it uniquely locks into a slower rhythm, reacting only once a second. Physicists call this discrete time translation symmetry breaking. This raises a heat paradox. If this material is constantly moving and being continuously bombarded by an outside laser, it should instantly heat up, generate entropy, and destroy its fragile structure. Answering why it doesn't melt is what separates a true time crystal from a simple mechanical trick. The answer requires us to look at the extreme rules of absolute zero. The secret lies in the quantum ground state. This is the absolute lowest possible energy configuration that a quantum system can occupy. Because the system is already at its energy floor, it physically cannot lose or transfer energy to the surrounding environment. This allows the particles to oscillate perpetually without any loss of kinetic energy. We are watching pure theoretical math cross over into physical reality. If you enjoy exploring the bleeding edge of physics with us, take a moment to subscribe. The first successful physical creation of this state happened at the University of Maryland. Researchers forced a chain of trapped ytterbium ions into alignment and manipulated them with alternating lasers to create a stable time crystal. By 2021, Google used its Sycamore quantum processor to achieve another major milestone. They maintained a time crystalline eigenstate order across a 20-qubit array for 100 consecutive cycles. A qubit is the basic unit of information in a quantum computer, representing an internal atomic spin. The scale and stability both rapidly escalated. In 2024, an experiment at Dortmund University in Germany maintained a time crystal made of indium gallium arsenide for 40 minutes. In less than 10 years, physicists moved from mathematical impossibility to successfully manufacturing a state of matter that exists permanently out of equilibrium. For 50 years, material science focused on engineering equilibrium matter, like standard metals and insulators. Today, researchers are shifting toward the design of materials that function permanently out of equilibrium. In late 2024, an international research team designed the first realistic photonic time crystals. Instead of applying this temporal repeating structure to physical atoms, they applied it to light itself. They created a medium that switches its optical properties quadrillions of times per second. When a light wave passes through this material, it actually pauses inside the crystal, while its intensity grows exponentially over time. This effect bridges the gap from lab theory to ultra-efficient optical computing and quantum memory. It also enables highly sensitive nanosensors, where the tiny amount of light emitted by a virus or a cancer biomarker can be captured and automatically amplified for immediate detection. Time crystals prove the laws of thermodynamics are not ultimate boundaries. They are invitations to discover new phases of reality hiding just out of sight.